Good morning, my name is Luis Alejandro Leiva. This is my English interview for heat transfer. We're gonna talk about forced convection in pipes. The exercise that we're gonna talk about is the 9114. Okay, this is the exercise. I'm gonna read it for you. Is hot water at 90 Celsius enters a 15-meter section of a cast iron pipe. The conductivity coefficient is 52 in international units, whose inner and outer diameters are 4 and 4.6 centimeters respectively, and an average velocity of 0.8 meters is divided by seconds. The outer surface of the pipe, whose emissivity is 0.7, is exposed to a cold air at 10 Celsius. In the basement, with convection heat transfer coefficients of 15 international units, taking the walls of the basement to be at 10 Celsius. Also determine the rate of the heat loss from the water and the temperature at which the water leaves the basement. Where we have here the picture for our exercise. The surroundings temperature is 10 Celsius, emissivity is 0.7, hot water at 90 Celsius, and a velocity of 0.8 meters divided by seconds. The length is 15 meters. We have to know that the roughness of the copper is 0.026 centimeters for our exercise. We have here hot water and a cold surroundings, meaning that the heat transfer is gonna be in this way, from the hot water to the surroundings. Then we have properties of the hot water at 90 Celsius. Density is 96.5.3. Specific heat is 4206. Thermal conductivity is 0.675. The dynamic viscosity is 0.315 times 10 wings minus 3, and Prandtl number is 1.96. Okay, to start our exercise, we have to know if we're gonna talk about for a turbulent or a laminar field. To determine this, we have to find Reynolds number. This is the equation. Reynolds is equal to velocity times the diameter of the pipe divided by the viscosity. But because we have here the dynamic velocity viscosity, we have to find this viscosity. That means that we have dynamic viscosity times the density. When we have this viscosity, we already have this viscosity, we can replace all the numbers in Reynolds. We have 0.8, that is the velocity, and 0.04, that is the density, divided by this big viscosity that we already found. When we have this, we have that Reynolds is 98,069.36. That is big, that the laminar Reynolds that we really want. That means that this Reynolds is a turbulent flow. When we have that, now we have to find if it's a developed or a developing flow. For that we have to find the leg for heat and the leg for the transfer. We have here the equation that is length is 10 times the diameter. This is the diameter, and here we have the relation. This leg is smaller than the leg that we have in the pipe, meaning that we have a full developed flue. Then we have to find Nusselt number. Nusselt number is related with these equations that say is 0.125 times the friction coefficient times Reynolds times Prandtl wings to 1 divided 3. We don't have here the fraction. We don't have here the friction coefficient, and for this equation we can find the friction. We have 1 times the friction square is equal to minus 1.8 logarithmic from 6.9 divided by Reynolds plus this number here is the coefficient of the roughness that we already have here. The roughness of the copper is 0.026 here, and then this is the diameter. And when we already find the friction coefficient, we can replace it in the Nusselt equation that we see here. We can see the 0.126 times 0.034, that is the friction, times 98.069.26, that is our Reynolds that we already found, and 1.96 times 1 divided by 3, that is our Prandtl. Nusselt is 521.6. Now we are gonna find the thermal resistance of the pipe because we don't know if the outer temperature is gonna be the same that the inner temperature. That's why we're gonna have to find the resistance of the pipe, the thermal resistance of the pipe. This is the equation for conductivity resistance, and we have the outer and the inner diameters. Those are here, and then we have this coefficient that is the coefficient of thermal conductivity for the pipe, that in our description of the example say that is 22, and the complete leg. When we have all this replaced in the equation, we know that the thermal resistance of the pipe is 2.85 times 10 wings to minus 5. This number and this resistance is not big enough to make a difference in temperatures of the outer and the inner temperature. Therefore, we're gonna use the same temperature that the initial temperature that the water have is 90 Celsius. The outer area, this outer area, we're gonna find it because we're gonna need it for the next steps. Outer area is P times diameter times leg. We replace all of them, but we have to remember that because is the outer area, we're gonna use the outer diameter. And now we have area for 2.160 square meters. When we already have all this, now we're gonna find the rate of heat lost from the water. This is the first question that we are gonna answer. We know that all heat transfer is the transfer for radiation and transfer for convection. First, we're gonna find the transfer for convection. This is the equation for transfer for convection. Transfer for convection is convection. Convection coefficient times outer area times difference between the temperatures. Okay, we know that 15 is the convection coefficient. The area we already found it here, 2.168, and the difference between the temperatures, that is the superficial 90 Celsius minus 10 Celsius, making our convection coefficient of convection 2601.6 watts. Now we're gonna find the heat transfer for radiation. That is this equation. In this equation, we can see that we have here two different numbers. First, this one is the emissivity that is already exposed in the description of the problem. Then we have this number that is a Stefan Boltzmann constant. This constant is for international units 5.867 times 10 wings minus 8. Okay, now we know all this all this data. To replace it in the equation is 0.7 times 2.168, that is the superficial area, for the constant that is 5.67 times 10 wings to minus 8, and the difference of these temperatures that have to be in Kelvin, that is temperature in the superficial minus temperature in the surroundings, wings for each one. Okay, we have to have these temperatures in Kelvin. Is really important, because the Stefan constant have this unit in Kelvin. Okay, now for mathematics of this equation, we know that the radiation coefficient is 943.42 watts. Okay, now we can find the total heat rate of heat lost, and we have here 2601.6 plus 943.42 watts, making our rate of the heat lost in total for 3545.02 watts. Okay, now we're gonna answer the second question, but first we have to find the flow mass. The flow mass is making this equation. This equation says that the flow mass is equal to density of a transversal area times the velocity. This time, this transversal area is P times density divided by 2 square. Okay, now we can replace all these datas, and we know that the mass flow is 0.95 kilograms by seconds. Why we had to find this mass flow? Because in the next equation we're gonna use it here. This equation is to find the temperature at which the water leaves the basement. Is this temperature. That means that we have to find this equation and replace in this equation all this data. Okay, initial temperature was 19. The heat transfer was 3545.002. The flow mass was 0.95, and specific heat was 4206. Now we have to make the math, and we have the temperature at which the water leaves the basement was 89.13 Celsius. Okay, that this is the second answer for the question, and that's it. Thank you.